Section 3.5, Introduction to Functions and Function Notation. Before we talk about a function, we have to know something about a relation. The definition of a relation is any set of ordered pairs. Sometimes we will know how they're related, sometimes we don't, but any set of ordered pairs is a relation. Now, what is a function? A function is a correspondence between a set of input values and a set of output values, such that each input value corresponds to exactly one output value. It's a little confusing when you first read it. So what does that actually mean? Well, to be a function, all you want is for your x values not to repeat. Your x values cannot repeat. That's what this definition is stating. We don't care if the y values repeat, we just don't want the x values to repeat. Now, if we look at the set of all input values, the set of input values is called the domain. And the domain comes from your x values. The set of all output values is called the range. And the range comes from the y values. So down below you see a function box. This is what I call a function box. We're going to take some input value, plug it into the box, and that's my function box. The function is going to do something to it, and then what comes out is the output. So the input values come from the domain. You take an input value, you plug it into your function box, and what comes out is going to be the output. So let's look at some examples. We want to find the domain, the range, and state that the relation is a function. Looking at number 1, we have ordered pairs 1, 5, 2, 4, 3, 3, and 4, 2. So when we talk about the domain, we want to find the x values. The x values are 1, 2, 3, and 4. So my domain is 1, 2, 3, and 4. Let's find the range values. The range values come from the y values, which are 5, 4, 3, and 2. So my range values are 5, 4, 3, and 2. Then at this point we need to decide, is this relation a function? So going back to look at our x values, we see that each x value was only used once. So yes, this relation is a function. Looking at number 2, we have ordered pairs 2, 2, 3, 2, 5, 3, and 3, 4. Finding our domain, we look at our x values, 2, 3, 5, and 3. We don't have to write it again if it repeats, so we'll just keep it as 2, 3, 5. Now we need to find our range. Our range values come from the y values. Our range values are 2, 2, 3, and 4. Again, we don't have to write it twice if it repeats. So my range values are 2, 3, and 4. Now we'll decide, is this relation a function? Did any x value repeat? It did. 3 went to 2, but 3 also went to 4. So this is not a function, but we have to state why. Because x equaling 3 repeated. So make sure you say why something is or is not a function. It is a function if the domain does not repeat. If one of the values repeats for the domain, then it is not a function. So number 3, the ordered pairs are 10, 5, 25, 35, and 45. So what's the domain? The domain are just the x values, 10, 20, 30, and 40. The range values come from the y values, and there's only one range value. It's a 5. So now we'll decide, is this relation a function? Looking at just the x values, 10, 20, 30, 40, we see that the x values did not repeat. So yes, this relation is a function because the x values did not repeat. We don't care that the range repeats. We don't care that the y repeated. We just don't want the x to repeat for it to be a function. Determine the domain and the range of the relation, then determine if it is a function. Given ordered pairs, we just choose every x value to find the domain and every y value to find the range. But given a graph, it's a little more challenging because of all the numbers that can be used on a coordinate plane. So looking at number 4, we have this graph. It's an absolute value graph. If you know that, great. If not, don't worry about it. But how do we figure out the domain? Well, the domain has to be what x values did you use. If I say looking at -2, 0, I definitely used -2, 0. But I also used -3 because it went up to 1. I also used -4 because it went up to 2. -5 went up to 3. And all the numbers in between I used as well because all of them will go up to a number on the graph. So if I keep coming out to say -10, I will use that x value. So if you see that this arrow continues, my domain is going to go from -infinity all the way to +infinity because every x value is being used. Whatever x value I choose, if I go up, I will eventually hit my graph. Just know that your domain has to go from left to right. So make sure when you write interval notation, you go left to right. We never include infinity because we can never get there, so always use parentheses on infinities. Now let's talk about the range. The range has to go from bottom to top, and we look at our y values. If I look at y value of -8 and I go back and forth, I will never hit my graph. If I look at -6 and I go back and forth, I will never use that y value. I finally start using the y value right at this point at the y value of 0. And if I continue drawing lines horizontally, I will see that I will use all these y values up to where? Up to infinity. So my range would go from 0 to infinity. We do get to include the 0 because we did include that point. However, again, we do not include infinity, so use a parentheses. How will we determine if the graph is a function? We'll do something called the vertical line test. I'm going to let you look up the vertical line test in the book or online if you'd like and fill in that piece down there. But what does the vertical line tell us to do? The vertical line says for every vertical line you draw, if it crosses a graph at only one point, your graph is a function. So let me clean up this graph for a second. So I'm going to get rid of all that. If I draw a vertical line, how many times did I cross my graph? Just once. If I draw another vertical line, how many times do I cross the graph? Just once. What that is stating is that for every x value, I'm only using it once. So therefore, this graph is a function. Why? Because it passes the vertical line test, which means my domain does not repeat. So let's begin again with domain and range on number 5. On number 5, let's talk about the domain. Again, the domain must go from left to right. If I say look at -9 and I go up or down, I will never hit my graph. At -7, I will not hit my graph, but I will start hitting at -6, and I continue hitting all these x values until I get to +6. We do get to include those points, so from -6 to +6 is my domain. Now my range will go from bottom to top. So bottom to top, when I start down here and I go back and forth, I don't hit my graph. I finally start hitting my graph at -6, and I'll continue hitting my graph all the way up to +6. So you'll see that all these horizontal lines continue to hit your graph on two different sides. So my range will also go from -6 to +6, again including those points. Clearing the graph one more time, let's talk about, is this graph a function? How do we determine that? We look at the vertical line test. The vertical line says draw a vertical line. If it crosses a graph more than once, it's not a function. So I can definitely see that this vertical line crossed my circle twice. So that means this x value right there was used twice. It went up to that y value and down to that y value. So this is not a function. Why? It failed the vertical line test. Therefore, that meant my domain repeated. So definitely not a function. So now let's talk about function notation. When a function can be written as an equation, we use function notation. We call this f of x. It's not multiplication. I know parentheses sometimes means to multiply, but this is function notation, f of x, or f evaluated at x. When you see function notation f of x, you can think of it as y equaling x plus 3. Now, f of x could be y, but y cannot just change back into f of x. So make sure you understand with function notation, you can think of it as y. Why are we using function notation? When we know that something is a function, we know that the domain does not repeat. So we have some extra and added information there. If we just see y equals, we're not sure. But when we see f of x equals, we know we have a function. So f of x is another symbol for output and always represents the range. So when you see f of x, you can think range values. X is called the independent variable. And y is called the dependent variable. So we choose a value for x, we plug it in, and we find our value for y. Let's try some examples. Find the indicated function value. F of x equals 6x minus 2. So A says to find f of 1. What does that mean to do? That means your x value is 1. So plugging in an x value of 1, you get 6 times 1 minus 2. Well, 6 times 1 is 6, and minus 2 is 4. So f of 1 is 4. Remember, f of 1 is stuck together. It's not multiplication, so don't think you have to do anything with that. That is function notation. But I would like for you to make a connection between function notation and ordered pairs. If x went in as 1 and y came out as the 4 value, like my function box on that previous page, 1 went in, 4 came out. So as an ordered pair, my ordered pair would be 1, 4. I don't want you to write it as an ordered pair, but I do want you to make a connection that function notation could be written as ordered pairs. Now let's try B, f of 0. That means plug in x being 0. So we get 6 times 0 minus 2. Well, 6 times 0 is 0, and minus 2 is negative 2. So that tells me that f of 0 would be negative 2. Again, making a connection to ordered pairs, my ordered pair would be 0, negative 2. Finding f of negative 1. Again, we plug in x being a negative 1. So we end up with 6 times negative 1 minus 2. Well, 6 times negative 1 is minus 6. Minus 2 would give me a negative 8. So f of negative 1 would equal negative 8. Again, think about what's happening. The x value is going in as negative 1. The y value coming out is negative 8. Part D says find f of t minus 3. Well, that means this whole t minus 3 is x. So plugging that in, I get 6 parentheses t minus 3, close the parentheses, but I still have minus 2. Distributing in the 6, we get 6t minus 18 minus 2. So we end up with 6t minus 20. So f of t minus 3 is 6t minus 20. Looking at number 2, we have f of x equaling the square root of 4x minus 2. We start off with the same way of finding what the x value is. The x value is negative 1, so f of negative 1 says plug in a negative 1 in for x. So anytime I do a substitution, use parentheses. So 4 times negative 1 minus 2. Well, 4 times negative 1 is a negative 4, and negative 4 minus 2 is a negative 6. Now I put that one on here because we are going to get into imaginary numbers later. But if you haven't heard of imaginary numbers now, you're going to just say this is not a real number. Not a real number. We'll get more into depth later on square roots. So I'm going to give you some answers for the next few problems. Try them out and see if you can get the correct answer. F of 1.5 actually turns out to be 2. So make sure you plug that in and get 2. F of 3 is going to be the square root of 10. You can't simplify the square root of 10, so you can leave it as is. And f of a is just the square root of 4a minus 2. Again, plug those in and make sure you can get those correct answers. Number 3. f of x equals x minus 2 over x squared minus 9. If you look closely at f of x, you're going to see we have to plug in two places for x. A says find f of 4, so that means x has to be 4. When I plug in a 4 on top, I get 4 minus 2. In the denominator, I get 4 squared minus 9. You have to plug in x being 4 wherever you see x. Really did not need the parentheses on top, but I always use parentheses when I substitute, and 4 minus 2 is 2. 4 squared is 16 on bottom, and so I get 16 minus 9. So I end up with 2 over 7. So what does that mean? That means that 4 went in and 2/7 came out. So f of 4 is 2/7. Let's try f of negative 1. Plugging in a negative 1 on top, I get negative 1 minus 2. On bottom, I get a negative 1 squared minus 9. Negative 1 minus 2 on top gives me a negative 3. On bottom, negative 1 squared is positive 1, and I still have minus 9. So I end up with negative 3 over negative 8. Well, two negatives make a positive, so I end up with 3/8. So f of negative 1 is 3 over 8. I'll give you the answer to f of 3. F of 3 is going to turn out to be 1 over 0. Something should go off in your mind when you see a 0 on bottom. Are we allowed to have 0 in the denominator of a fraction? No, we can never have 0 in the denominator of a fraction. We've lost our foundation. So f of 3 is undefined. You can't figure out what that value is because we cannot divide by 0. So f of 3 is undefined. Lastly, f of a, when I plug in an a on top, I get an a minus 2. When I plug in an a on bottom, I get an a squared minus 9. Yes, you could factor a squared minus 9, but nothing else is going to be able to cancel from that, so we can leave it as a minus 2 over a squared minus 9. So this last problem is just to see how many students truly understand function notation. Number 4 says graph f of x equaling 4x minus 1. I really give my students about a minute in class to figure out, can they graph this? But I will let you pause me and see if you can graph it before I continue. So, if we really truly understand function notation, we know that f of x just represents y, and y is 4x minus 1. This is in the form of y equals mx plus b. So I can graph y equaling mx plus b by starting at negative 1 on the y-axis. My slope is 4, which tells me to go up 4 and over 1. So from the intercept, I'll go up 4 over 1, up 4 over 1. And there is the graph of f of x equaling 4x minus 1.